Good evening, and welcome to our next set of lectures. We're going to do some more work with enthalpy, and we are going to play around with the fact that it is a state function. Now, you'll recall that for a state function, it doesn't matter how you get where you're going, just that you get there. So if you were to go 5 miles west, then 5 miles north, that would get you to the same place as going 5 miles north, then 5 miles west. Enthalpy works the exact same way. It's a state function, meaning it doesn't matter what path you take to get somewhere, just so long as you get from point A to point B. So let's say you have the reaction of hydrogen and oxygen making water, and you want to measure the enthalpy of this reaction, or the enthalpy change, I should say, for this reaction. Now, the problem is that hydrogen and oxygen combining to make water is a very rapid reaction. That is to say, it goes boom. And explosions are notoriously difficult to measure. So you might try to do it slowly with a controlled set of reactions. And that's where Hess's Law comes into play. So let's go ahead and take this more or less completely made-up hypothetical set of reactions. You combine sodium with hydrogen to make sodium hydride, and that's reaction 1. Then you combine sodium with oxygen to make sodium oxide, and that's reaction 2. Then you take those two, sodium hydride and sodium oxide, and you combine them together to make sodium and water. Like I said, hypothetical made-up reaction. I'm pretty sure you couldn't actually do this. It's just sort of pretend it's a hypothetical. And the thing is, when you look at this, if you add these three reactions together, you should, assuming you balance them, you should get the reaction down at the bottom. And this is our first example of doing a Hess's Law sort of problem. We need to make the elements show up where they need to be in the order or the number they need to be. So you look at the first reaction, it has 1 hydrogen, we need 2, so we're going to go ahead and multiply the first reaction by 2. Not only does that turn 2 sodium into 4 sodium, 1 hydrogen into 2 hydrogen, and 2 sodium hydride into 4 sodium hydride, it also doubles the amount of energy produced or consumed by that reaction. Okay, remember that the enthalpy change for a particular reaction is per unit of reaction. You double the number of times the reaction is occurring, you're going to double that particular energy change. So double the reaction, double the enthalpy change. That's important. Got to remember that, or things will get all wonky and you'll end up dying alone. And for reaction 2, it has the appropriate number of oxygen, so we multiply it by 1, and we don't have to change anything about that. And for the third reaction, we need more water, so we need to multiply that reaction by 2, which changes all of the numbers in reaction 3 by multiplying by 2, including the enthalpy change. And it wouldn't be a nicely put together problem if there wasn't some way to double check your work. So let's go through and make sure that these three actually add up to the reaction down on the bottom. And that means canceling anything that appears on both sides of the reaction arrow. Okay? If it's a reactant on one side and a product on another, we get rid of it. And the first thing we see is that sodium oxide goes bye-bye. We have 2 on the left down here in reaction 3, and 2 on the right up in reaction 2. And next we get rid of sodium hydride. There are 4 sodium hydride amongst the reactants in reaction 3, and 4 among the products of reaction 1. And then we can get rid of the sodium, because there are 8 sodium in the products, and we have 4 sodium in each of the reactants for reaction 1 and reaction 2. 4 plus 4 equals 8. They all cancel out. And then you go ahead and you add up everything that remains. You get hydrogen plus oxygen on the left, making water on the right in all the numbers we need. Yay! And Hess's law is a state function, just as, matter is a state function. So the enthalpy of reaction for hydrogen and oxygen combining to form water is going to be the same thing as 2 of reaction 1 plus 1 of reaction 2 plus 2 of reaction 3. And so the sum of 2 plus 1 plus 2 is the same as the enthalpy change for the final reaction down there on the bottom. Remember, it doesn't matter if you go north, south, east, west, what have you, so long as you get from the same starting point to the same ending point, the change in enthalpy is going to be the same. 2 plus 1 plus 2 is the same as that reaction down there at the bottom. And that is how you can use Hess's law. You could take 3 somewhat random reactions, multiply them, divide them, add and subtract, so long as you can get from point A to point B. That will give you the enthalpy change for the final reaction. Now, let's go ahead and do a slightly more realistic example by playing around with acetylene. So, the reactions in question, well, up top, we have the 3 reactions whose enthalpy changes we know. The first reaction up here is acetylene plus oxygen making CO2 and H2O, just the combustion of acetylene. Nice and straightforward. Very exothermic. It releases it just releases 1,300 kilojoules per mole. So the enthalpy change is negative 1,300 kilojoules per mole. Enthalpy change, exothermic, is negative. The next 2 are a little bit simpler. Just carbon and oxygen to make CO2, hydrogen and oxygen to make H2O. You may have noticed that we're starting to see some fractional coefficients. Playing around with Hess's law is when you start to see that sort of thing, and it's only okay when you're doing Hess's law problems. For balancing reactions, with one exception, you never ever do that. For Hess's law, you can get those as results. Okay. Now, the reaction we're looking to find the enthalpy change for is down here at the bottom. 2 carbon plus hydrogen to make acetylene. How can you build it from the simple elements? What is the enthalpy change for that reaction? Now I'm going to switch back over to Microsoft Paint and see if we can't work through this problem. We can. We definitely can. Now, the first thing I'm going to do here is I'm going to recopy all of the information so I don't have to keep flipping back and forth between different slides. It's just our 3 reactions in different colors because that's fun. You'll notice I've also made the arrows line up somewhat. It makes it easier to notice what's on the reactant side, what's on the product side, so that we can cancel things out. The next thing we do, once we have our reactions set up all nice and pretty, is we have to rearrange, that means flipping and multiplying our known reactions, in order to get everything in the numbers we need and in the locations we need. By which I mean to say, for example, down here in our unknown reaction, our goal, we have acetylene on the right-hand side among the products. When we look up at our known reactions, the building blocks, as it were, we see that acetylene is only in the first reaction, and it is on the reactant side. Okay? So it has the right number of acetylenes, but it's on the wrong side. We need it to be a product, which means we're going to need to flip this reaction around. So the reactants become products, products become reactants. And that is going to have an impact on the enthalpy change of that first reaction. In mathematical terms, flipping the reaction means turning reactants into products and products into reactants. We're just switching the direction of the reaction, that's all. So that means that we're multiplying the reaction by -1. Instead of going forward, it's going backward. When you do that, you also end up multiplying the enthalpy change by -1. The enthalpy change for the reverse reaction is just the negative of the enthalpy change for the forward reaction. If you go to the right 5 meters, then the reverse means going to the left 5 meters, or going negative 5 meters to the right. So when we look at this particular reaction, it's going to change, because we multiply by -1, to 2 carbon dioxide plus 1 water, producing 1 acetylene molecule and 5/2 oxygen molecules, with an enthalpy change of positive 1299.5 kilojoules per mole. And next up, we're going to go ahead and do the same thing we just did for carbon. We look at our goal reaction. We need 2 carbon on the left, 2 carbon amongst the reactants. We look up at our building block reactions, and we see carbon is only available in the second reaction. It's already on the left, which makes things a little bit easier. No need for multiplying by negatives. But we don't have enough, so we are still going to have to multiply. We have 1, we need 2. We need to multiply the reaction and the enthalpy change by 2. You do the reaction twice, then you're going to get twice the enthalpy change. So we multiply by 2, and the result is going to be that reaction 2 is changed to 2 carbon plus 2 oxygen yields 2 carbon dioxide with an enthalpy change of negative 787 kilojoules per mole. Now we look at our final piece of the puzzle down in the goal. We have hydrogen on the left. We only need 1. We look at reaction 3. We have hydrogen on the left, and there's 1 of it. So we don't need to do anything to that reaction. In mathematical terms, that means we are multiplying reaction 3 by 1. That just keeps it exactly the same. So hydrogen plus 1/2 oxygen yields water with an enthalpy change of negative 285.8 kilojoules per mole. Now, assuming that the building blocks have been provided correctly, that should add up to the goal that we're looking to get down at the bottom. And of course, we can double check that by making sure that everything we don't want cancels out. First up, carbon dioxide. Fairly straightforward. We have 2 carbon dioxide among the reactants up in reaction 1, and we have 2 carbon dioxide among the products down in reaction 2. If it's on both sides of the arrow, it cancels out, so those go bye-bye. Next up, also fairly simple, we have 1 water among the reactants in reaction 1, and 1 water among the products in reaction 3, so those go bye-bye. Oxygen is a little bit more complicated. You're going to have to reach back into the misty depths of time and remember how to add fractions together, or convert between fractions and complicated fractions, whatever those were called. And we see that 5/2 oxygen is the same thing as 2 and 1/2. And that means, well, we have 5/2, or 5/2 or 2.5 oxygen among the products up in reaction 1. We have 2.5 among the reactants in reactions 2 and 3, so our oxygen cancels out, leaving us with 2 carbon plus 1 hydrogen yields 1 acetylene. Yay! And since our 3 reactions add together to produce the goal reaction, that means that our 3 enthalpy changes now add together to produce our enthalpy change. The enthalpy change of the goal reaction is equal to negative enthalpy change 1 plus twice enthalpy change 2 plus 1 of enthalpy change 3, which means that, all told, the enthalpy change for the formation of acetylene from the elements carbon and hydrogen is 226.7 kilojoules per mole. And we've just about hit the 15-minute mark, so we'll go ahead and leave it there for now. When we come back in Lecture 6, we're going to talk about that number a little bit more and make sure that it makes sense.